Let's talk about rotating imbalance in rotating machines and structural dynamics perspective. Consider a single degree of freedom system consisting of a mass m supported by a spring with a stiffness k and damper with a damping coefficient c. The mass is constrained to move vertically. Assume something like this with a spring and a mass and a dashpot also with some dashpot. It's connected to the system. Okay, this is damping coefficient, this is the stiffness value, and this mass. Okay, it's constrained to move up and down only. Just assume like that. Attached to the mass is an unbalanced rotating mass. That radius eccentricity e, which rotates at a constant angular velocity. One thing you have to understand, like suppose if something is some mass, this kind of mass is rotating in angular speed omega, the speed is omega angular speed, it will have two accelerations. One is tangential acceleration, another one is centrifugal acceleration. Centrifugal acceleration acts towards the center, and that depends on the radius and this mass and velocity square. That's nothing but mass into radius into velocity square. That will be the centrifugal force that's acting towards this center. That's the one it's holding it. Now the tangential acceleration, it will be acting like this. That will be mass into radius into angular acceleration. It will come. Alright. So let's discuss about this one. To determine the vibration response of the system due to rotating imbalance and specifically steady state amplitude and phase of the vertical displacement. Total mass is m, unbalanced mass is small m. Is a small portion of that is m is much less than capital M. Eccentric mass rotates at angular velocity w produced by harmonic excitation due to the centrifugal force. The system behaves linearly and can be modeled as a single degree of freedom mass damper system. System coordinates. Let's let x of t be the vertical displacement of the mass m, excluding the eccentric mass from the static equilibrium position. The displacement of eccentric mass is x of t plus e into sine omega t. Motion of equation will be the spring force, damping force, and inertia force due to eccentric mass. Inertia force due to eccentric mass will be, this is the eccentric mass, then this is the displacement x plus e plus sine omega t. Inertia force of resisting mass is m minus m remaining mass into x double dot. Net dynamic equation will be m minus m dot cx and kx and m into d squared by dt squared into e power sine omega t. That displacement we are what we are doing, displacement 2 times if you derivate it, like differentiate, you will get the acceleration, right? That's why this d squared x by dt squared is nothing but acceleration. Acceleration, how will you define? You double times you integrate it. D squared x by dt squared is the acceleration for the displacement, right? Rate of change of velocity, rate of change of displacement is velocity, rate of change of velocity is acceleration. That's why this value it comes like this. X is nothing but this value, right? Displacement of that small mass. So you are getting this one. So d squared by dt squared e sine omega t, we can see calculate the right side acceleration. E, you can take it out, minus omega squared sine omega t. That's going to be the force acceleration value. Then if you multiply with the mass, it will come force. Therefore m minus m net mass into acceleration cx and kx into m e omega squared sine omega t. And the most reciprocal small m is much less, so m minus m will be approximately m only. So mx double dot cx into kx equal to m e squared sine omega t. Natural frequency and damping, omega n equal to k square root of k by m. Undamped natural frequency, this is the damping ratio. Forced vibration response, we can get it from the equation. This is the force. harmonic force amplitude. The steady state solution displacement can be like this: x of t equal to capital X sine into omega t minus phi. X we can get it from this equation, p of x divided by 1 minus omega by omega square, that is a beta ratio, and 2 into omega and rho into omega by omega and whole square, that becomes rho, right? So it becomes like 1 minus beta squared whole square plus 2 rho beta whole square, and we know the phase difference, it's a tan inverse of 2 times rho b divided by 1 minus beta squared. So beta is the bit frequency, so normalized amplitude expression, multiplying numerator denominator by capital M, using rho is m by m, noting k equal to m into omega square. So normalization highlights the dependency of displacement amplitude on system parameters. Physical interpretation: at low frequencies beta is much less than 1 means amplitude is small. Near resonance amplitude peaks dramatically but limited by damping. High frequency amplitude decreases inversely with the square of the frequency. Phase angle shifts from 0 to 180 degrees as frequency passes through resonance. Complete time response will be, including transient terms, e power minus rho omega n t a sine et b cos omega t plus x plus sine omega t. This one is the steady state response. This is the transient response. Transient disoed because of the presence of damping. Omega d, that we know, that we can calculate. A and b depends on the initial conditions. Transients decay exponentially, leaving steady state vibration described by x into sine omega t minus omega phi. So the rotating imbalance force is equivalent to harmonic excitation me into omega square. The system vibrates at the forcing frequency. Amplitude of phase is determined by the standard force vibration relations of damped. So we can see some plot and phase angle versus frequency ratio. Complete solution for displacement will be transient response that's due to initial conditions with the decays exponentially, steady state forced response at frequency, forcing frequency omega. That forcing frequency is this value. Transient is decaying exponentially. That decay exponentially is, this is the one. Omega equals square root of given natural frequency. It's a damping ratio. Damped natural frequency is a steady state amplitude from worst vibration arches. This is, and phi is the phase angle between the force and displacement. This is the phi angle. How the force is going and how displacement is following. Are they in sync or out of sync? 90 degree shift, phase shift, that comes from this phi. C1, C2 are constants determined by initial conditions. Express steady state amplitude, we can calculate m e omega squared by k square root of 1 minus this value. From here we can calculate the phase angle. This is the transient term e power minus 180, right? And steady state term, it includes this forcing frequency and this force amplitude. This is the force value. Clean final formula is this transient plus steady state. The first part represents free vibration with decaying term. The second part represents forced vibration due to rotating imbalance. This is the second part. Phase depending on the system properties and force and frequency. Let's have a group discussion between engineers and trainees. Alright team, today we will talk about rotating imbalance in machines. Who can tell me what causes vibration in rotating machine? Is it because the mass is not evenly distributed? Even a mass is off center, it creates imbalance. Imagine a small weight stuck at a distance of e from the center. So as it spins, it pushes the machine up and down. That pushes harmonic force. It goes up and down with rotation speed omega. How do we model the machine's response? We use the spring mass damper system. The mass moves vertically and the imbalance force X excites it. So what's the equation for this system? The motion is, this is the mass damping stiffness, and me omega squared into sine phi t. We know here m is the mass, e is damping, k is stiffness. What happens when the rotation speed matches natural frequency? Then that becomes resonance. The vibration amplitude grows very large but limited by the damping. How do we find the vibration amplitude? By solving the forced vibration equation, the amplitude is x, that's the magnitude of the forced vibration. And so if you increase the damping, the vibration decreases. Yes, that's proportional to inversely proportional to the damping. That's why machines have dampers to reduce vibrations. Can we stop vibrations completely? No, but we can control them so they are safe, not damaging. Thanks, this really helps. Today we are diving into machine vibrations. Why is vibrations a big deal in the rotating machines? Can anyone tell me why? Because machines have moving parts that are not perfectly balanced. They are not always perfectly balanced. Even small imbalance can cause vibration that affects performance and cost wear and tear over time. How do you understand these vibrations? Just by watching the machine shake. We use mathematical models and measurements. The basic model is a spring mass damper system to represent the machine's moving part. How does this model work? Think of a mass M, a spot that moves. It's connected to a spring with stiffness K and damper with damping C. When the mass moves, the spring tries to pull it back and the damper resists the motion. The mass, when it tries to move, the spring tries to pull it back and damper resists its motion. Where does the vibration come from then? From the external forces. If in rotating machines, one common source is rotating imbalance. Imagine a small mass M stuck off center at a distance c spinning at an angular velocity omega. This creates centrifugal force that acts like a harmonic force on the system. What does that force look like mathematically? It's a sinusoidal force. It's a sinusoidal force. Omega is the rotation speed. How do we write the equation of motion with this force? The equation of vertical motion is mx double dot cx kx and me omega squared into sine omega t. That looks like a forced vibration equation. Exactly. The left side describes the machine's natural resistance. So that left side is natural resistance, that mx double dot mass resist acceleration, and c into x dot, that damping resists the force velocity it resists, and k into x spring resists the motion. So this part is natural resistance. On the right hand side, that me omega squared into sine omega t is right. That's the forcing due to imbalance, that m is due to imbalance. What happens when the forcing frequency m omega is close to the natural frequency omega n? That's resonance. The system's response becomes very large, potentially causing damage. How can we predict the vibration amplitude? How much vibration is going to happen during the vibration? That we can predict by solving the forced equation. By solving this equation, the steady state amplitude is me omega squared by k into square root of 1 minus omega beta squared whole squared plus 2 into rho into omega beta whole squared. C into 2 by omega n. That's a damping ratio. This damping ratio is nothing but actual damping by 2 into m into omega n. Critical damping. So if the damping is 0, what would happen? The amplitude would go infinity at resonance. If the damping is 0, the amplitude would go to infinity at resonance. Theoretically, yes, but in real machines, there's always some damping, preventing infinite vibration. Can you reduce the vibration by adding more damping? Yes, absolutely. More damping means lowers the peak amplitude and spreads out the resonance peak. So it will not be like this. It will be like this. If more damping means the peak will be spread out. It spreads out the resonance peak. What about other source of vibration besides imbalance? Examples include misalignment, looseness, gear machine, bearing force. Each has unique vibration signatures. How do we tell them apart? By Vibration analysis, measuring vibration signals, analyzing frequency content using tools like FFT, fast Fourier transform. If we have the vibration signals, analyze the signal for the frequency content using FFT. How much is the frequency content from the signal? So what does the fast Fourier transform do? It breaks down the vibration into signal. This is the vibration signal. Okay, this vibration signal is breaks down into frequencies, f1, f2, f3, like that. It is breaking down the signals into frequencies, and we can find out which frequency is dominant related to this false. This if imbalance creates vibration, rotation, frequency. What about the gear false? What is vibration? Gear means frequencies, multiples of rotation speed on the side bands. Is this by vibration monitoring is key in improvement maintenance? Yes, it helps us detect faults early and plan maintenance avoid breakdowns. How often should machines be checked? That depends on the criticality of the machine, but regular monitoring is essential, especially near frequency and resonance condition. What about the transient vibrations? Transient vibrations occur during the startup or shutdown. Transient vibrations occur. That changes when conditions change rapidly. We analyze these to catch any sudden issues. Vibration analysis helps us understand the machine health. Imbalance is a simple but yet common cause of vibration. Proper modeling measurement analysis keeps the machine running smoothly. Let us focus on the forcing function caused by imbalance in the rotating machine. What exactly is the forcing function? Is the external force that makes the system to move or vibrate. So in rotating machine, what causes this force? An unbalanced mass rotating around the shaft center. How does that create force? Imagine a small mass m attached to the distance e from the center, as it spins. It pulls outward due to centrifugal force. Is there a force constant? No. It changes in direction as the mass rotates, so it's a periodic harmonic force. How do we express this mathematically? The centrifugal force is mu squared sin omega t. It's the angular velocity, t is the time. Why is there a sine function? Because the force in direction changes as the mass rotates. The sine function describes this oscillation over time. What is the meaning of omega squared in the formula? It's because the centrifugal force depends on the square of the speed, rotation speed. Centrifugal force depends on the square of the angular speed, rotation. What about the distance e? That's the eccentricity. How far the mass is from the rotation center. Larger e means more imbalance and bigger forces. Is the mass m always small? Yes, usually yes, related to the total mass, but even small mass can cause big vibrations if spinning fast. Does this forcing function act on the whole machine? It acts on the rotating part and causes the entire machine to vibrate. Forcing function act on the whole machine. It acts on the rotating part and causes the entire machine to vibrate, especially the part supported by the springs and dampers. So this force is what excites vibration. The forcing function drives the motion of the system. Can this force change if the machine speed changes? Force amplitude changes with omega square. Frequency of the force is exactly the rotation speed. What happens at resonance? When the forcing frequency omega equals to the system's natural frequency, the machine vibrates a lot because the forcing function matches the system's natural rhythm. Can we control this forcing function? We cannot remove the imbalance force completely without balancing the mass, but we can reduce its effect by damping or resistance speed. How do we measure this forcing function? Yes, we infer it by measuring the vibration and knowing the system properties. Then back calculating the force. Remember, the forcing function from rotating imbalance is sinusoidal force with the amplitude me omega squared and the frequency omega. It is the main cause of vibrations in many rotating machines. And note that now that we understand the forcing function, let's talk about how to solve the equation of motion of the system. What's the equation again? This is the equation. And x of t is the displacement of the mass. That this looks like a force vibration problem with damping. The left side models the machine's natural response. This is machine's natural response. Right side is the forcing function from the rotating imbalance. This is the forcing function from the rotating imbalance. How do we solve this equation? Homogeneous equation is the system's free vibration without forcing. particular solution is the steady state vibration caused by forcing function. What does a homogeneous solution look like? It's a homogeneous solution looks like free vibration. This describes damped free vibration. Is a solution. Omega is natural frequency and damping ratio. Eta is damping ratio and damped frequency, and A and B depends on initial conditions. On the particular solution, since the forcing function is a harmonic sine function, we look at the particular solution in the form of x p of t is x into x is the steady state amplitude and phi is the phase angle lag between the force and displacement. What's the distance, force and displacement? What's the lag? How do you find x and phi? By substituting x p of t, the original equation, in terms of, then we can find x and phi. X depends on the forcing frequency related to the natural frequency. That y omega is near to omega, x peaks. That's resonance. What does the phase angle tell us? It tells us how much vibration lags behind the forcing function. How much vibration lags behind the forcing function. At low frequency, displacements nearly in phase with force, near resonance. Lag is 90 degrees, and high frequency is nearly out of sync. How do we write the full solution? Homogeneous equation, particular solution. This is the homogeneous free vibration. This is the forced vibration. What happens over time? The transient part decays due to damping. After some time, only steady state vibration remains. So the machine eventually vibrates at the forcing frequency. A steady state vibration is synchronized with the imbalance rotation. What are the initial conditions? They affect the constancy and being transient solution. Initial conditions affect the transient conditions only. Usually after enough time, the transients fade away, steady state dominates. Can you summarize the key points? Combined transient free vibration and steady state force vibration as amplitude depends on the imbalance, magnitude, speed, damping, stiffness, response, amplification, near natural frequency, source, phase shift between force and response, diode, transient diode, damping, leaving steady oscillations at force frequency. How imbalances cause vibrations we can predict and control, and this is analysis foundation vibration. Why do we say mass is eccentric? Let's analyze the imbalance force more deeply. We model rotating part having small eccentric mass radius E from rotation because it's offset from center line instead of rotating perfectly around its center mass, shifting, forcing. How do we express position of this eccentric mass? Assuming the rotor spins at a angular velocity, the position of vector mass is E cos omega ti, E sin omega ti. I and j are the unit vector horizontal vertical directions. Velocity is the derivative of time derivative, whatever the acceleration is having a second derivative. This means acceleration points inward and toward the center, centripetal acceleration. How does this relate to the imbalance force? Mass experience of force. So the force vector rotates at angular speed omega. This force is continuously changing the direction, changing in the rotating plane, producing harmonic force. If you analyze in one direction, say vertical, how do we get the forcing function? Vertical component is one. The additive sign indicates the direction. So often we write this is the forcing function in vertical direction. What are the assumptions we are making? The imbalance mass is rigidly attached and rotates at the constant velocity speed. The system is linear. Displacement is small enough not to change dynamics. Gravity affects either the including static equilibrium or negligible vibration. Only one degree of freedom is considered. What about if there is a multiple imbalance in multiple planes, then the total forcing is the vector sum of components of each plane, possibly producing elliptical orbits or complex vibration. How does the forcing magnitude change with speed? Because the force is proportional to the omega square, increasing the speed quickly raises imbalance forces. That's why high speed rotors are very sensitive to imbalance. How does this force affect the system's equation of motion? It appears sinusoidal forcing term on the right hand side. This derives the force vibration response. Is this main cause of vibration rotation? Yes, imbalance is the main source of vibration for rotating equipments like motors and fans and turbines. How do engineers deal with this force practically? By balancing the rotor or adding or removing the mass to reduce eccentricity, or by using dampers or isolators to control vibration. To summarize, imbalance force is the rotating harmonic force. with the magnitude of this much m mu y squared and frequency equal to rotational speed. These force exercise structures must be accounted for in vibration analysis.